We don't have class on Thursday, so we got to make sure we get through all of centroids today so you can work on some problems. The tests, oh, well, I was about to say I'll have them back Thursday, but that won't do any good. Well, anyways, those will be graded by Thursday. The scores will be posted, and then I guess I'll give them to you next week. So we're talking about centroids. I gave the integral definition, and then I gave formulas that you could come up with from the integral for a bunch of simple shapes. Those are what we're going to use in this class. We're not going to use the integral definition. And then I was talking about how to build up the centroid of a complicated shape from simple shapes. We did one where we added two shapes. So using the sum formula, we did a shape like this. That's done. And now I want to do one where we're subtracting a shape. So you can think of it as removing material. So let's say that we have a big rectangle with a length of 2 meters and a height of 1 meter. And let's say that we remove a circle from that rectangle. So this is air, nothing. What's the centroid of this shape? By the way, the circle comes right up to the edges like this. You can tell that the radius of this circle is half. You know, the diameter is 1. Okay, so let's separate this up into a big outer shape. I'll call that body 1. And a small inner shape, body 2. And to use that summation formula, we need the centroid and the area of each of these two shapes. And since the centroid comes in the form of coordinates, we have to choose a coordinate system. It doesn't matter where you choose it, but I'll do it over here. Okay, so for the rectangle, area 1 is 2 times 1, so 2. And what are the coordinates of the centroid of the rectangle if you forget about the circle for now? Yeah, that's right. It's 1 over in the positive x direction, and then 0.5 up in the y direction. Yep. So x1, y1 is equal to 1, 0.5. And then for the circle, the area is pi times 0.5 squared, which is pi over 4. And what's the centroid of the circle? 1.5, right? The whole the diameter is 1, so the radius is 0.5, so it's 2 minus 0.5. But yeah, so 1.5, 0.5. And now for the sum formula, or for the centroid, the total centroid is equal to 1 over the total area. In this case, the total area is going to be the outer area minus the inner area. Times the area of the first one times its centroid. Minus the area of the second one times its centroid. And if you go through that calculation, you get something in decimals that's like 0.68, 0.5. Well, then if you look back, you can actually see that there's an axis of symmetry this way. Remember, to think about the axis of symmetry, think about being able to take this shape and fold it, and everything matches up. You could fold it along that blue dotted line. Everything would match up. And so that's an axis of symmetry. So that means that the centroid has to lie along that blue dotted line, which is at a y position of 0.5, and so our answer matches that. If we had noticed the line of symmetry before we started, we could have skipped the calculations with the y component.
But the line of symmetry, would that affect, because we have like the circle taken off, it's like rectangle without the circle.
Yeah, so for the axis of symmetry, just think of, like, if we carefully, if you cut out a rectangle in this shape, and then cut a circle out of the middle, is there any line where you could fold that shape and everything would match up?
Oh, yeah.
And it's still, even with that circle removed, it would still match up. The whole would match up. You know what I mean?
Yeah.
So it's an axis of symmetry still. All right. So now let's use that in a statics calculation. So let's say that we have this shape. It's connected to a pin joint at the top corner. Remove that circle. And then there's a roller at the midpoint that's in contact with the ground. And the mass is equal to 100 kilograms. And we want to know what are the reactions. This is 2D, yeah. If it was 3D, all of our centroid calculations would have to have a Z component too. Okay, so free body diagram. You got the shape. Now, where the centroid calculation comes into it is the centroid is where the weight force acts. That's somewhere over here. This whole length is 2, and the centroid is somewhere short of the midpoint, like this. Yeah, so the first of 2 reasons that we use centroid calculations is to figure out where to apply the weight force. The weight always acts at the centroid. We've kind of glossed over that up until now because we've had these simple shapes where, we're just applying things at the middle and that's all we had to think about. But with more complicated shapes, you have to put it at the centroid. I mean, it's always at the centroid, but yep. And so the weight is 100 times 9.81, so 981. And then at the pin joint, we have an unknown force vector, R. And then at the midpoint, on the bottom edge, we have the connection to the roller. I don't know, I'll call that F. One thing that's a useful thing to keep in mind, and it's going to come up more when we talk about distributed loads, is weight is always acting down. And if our components have the y-axis vertical, which one of the 2 centroid components is useful and which one is useless for applying the weight force? One of them just isn't going to come into it at all. The y component isn't going to matter at all because if you put it at the right x location, you can give it any y location and that's just moving the force along its line of action. It doesn't change the problem. So we could have just calculated the x component of the centroid and then just set the y component equal to 0 or 1,000,000 or pi or whatever. It doesn't matter. I wouldn't set it to pi. That seems kind of unnecessary. But 0 might be, Okay, so now let's calculate, fill out this table. So rho F moment. And, well, our origin in calculating those, in calculating the coordinates of the centroid was down here. We'd kind of prefer to have the about point up here. I guess let's do that. That's not too horrible. So let's put the about point here, where we have the most unknown forces. So what's the vector from the about point to where R is applied? Yep, that's 0. That's a warm-up problem. It's going to get harder from there. Okay, so the force vector is Rx, Ry. Cross product is 0. What's the row vector from the about point to where that weight force is applied? Yeah, you'd have to sort of recalculate, but we do know it has the same x position, And we don't care about the y position, so I'm just going to put this in as 0.680. That 0, we just don't care. And the force vector applied by gravity is 0, negative 981. And the cross product is negative 667.08. And then the last one is the reaction at the ground, the roller. What are the coordinates where that force is applied? Yeah, 1. This also, the line of action is like this, so the y position doesn't matter in this case. The real y position would be negative 1. We don't care about that one either. I don't know why I put it in this time. The force is 0, positive F. And the cross product is F. So now Newton's second law says Rx, Ry plus 0, negative 981 plus 0f is equal to zeros. Can't solve that yet. And then the moment equation says negative 667.08 plus f is equal to 0. And if you solve that system, you get f is equal to 667.08, and r is equal to 0 for x and 313.92 for y. And you can see that in doing this calculation of the moment produced by the weight force, if the x location of that centroid changed, that cross product would change, the moment would change, and so these values depend on the correct location for that weight force. Okay. If you move that weight somewhere else horizontally, you get different answers. Wrong answers. Okay, so that's the first use for centroids. The second one is distributed loads. And really, weight is a type of distributed load. But distributed loads are forces spread over an interval instead of acting, rather than acting at a point. For calculations, we always need to choose a point where we can treat it as a point force. We always need to represent distributed loads as point forces. So an example of a distributed load that you could see, if you have a beam, a cantilever beam that makes a fixed joint with the wall, you'll see problems where the external load is shown like this. And it says up here you have a value of 10,000 newtons per meter. Let's say this is 2 meters. Okay, so to do this calculation, you have to figure out how to translate what's given as a distributed load into a point force, and that involves two things: figuring out what the total magnitude of the force is, and figuring out the location where you could put that point force to make it an equipolant system. Okay, so we need two things. Total point force, and second, where the point force must act to be equipolant. So the behavior is the same. All right, so before I talk about how to do this, and really how to do it is pretty simple. You have to understand kind of what this is getting at. So what is a distributed load? I think the best way to think about it is in terms of an analogy with like speed or velocity. So let me put together these two columns. On the left column, let's say, and actually, let's change that to velocity. Who talks about speed? Okay, so on the left, distributed load versus point force. And on the right is velocity versus displacement. And this displacement, think of that as the instant, not the displacement. There's no such thing as instantaneous displacement. Stupid! Oh. This velocity is an instantaneous velocity. Okay, so first, what's the meaning of, so say that an instantaneous velocity is like 30 meters per second. Okay? So first of all, that means if the instantaneous velocity were held steady over 1 second, that's how many meters you would travel. That's the number of meters of displacement, right? If you're going 30 meters per second, and you stayed 30 meters per second for a full second, you'd go 30 meters, right? Distributed load is the same way. If the distributed load were constant, over 1 meter, that's how much total force would be applied. Okay, second, at a single location, how much displacement is provided by a velocity? Well, none, right? Like in a single instant, you can have an instantaneous velocity, but you don't go anywhere in an instant. So at a single instant, the instantaneous velocity is finite. But the displacement is infinitesimal. And again, that's the same with distributed load. At a single point, the distributed load is finite. But the total force is infinitesimal. Okay, so let's go up to this picture here. So what this is saying is this linear function represents the distributed load anywhere along here. So right here, there's a distributed load of 10,000 newtons per meter. Right here, there's a distributed load of 0. Right in the middle, there's a distributed load of 5,000 newtons per meter. At every point, there's a finite distributed load. But if you want to know how much force is applied, say at this point here, it's infinitesimal. You can't get any force without having a distributed load applied over an interval. Okay, that's kind of the heart of the analogy between velocity and distributed load. And so the third one is instantaneous velocity only leads to a displacement over a finite time interval. And then for distributed load, the distributed load only leads to a force over a finite length interval. Any questions about that? Okay, so for calculations with distributed loads, first we need the total force applied by the distributed load. And that's the area of the shape. And second, we need the location of the point force. The location where the point force is applied. And that's the centroid of the shape. One thing.
Use the shape that the distributed load makes, or the shape of some object it's after on?
The distributed load. So in this case, the shape would be that triangle.
Okay, so it would be the centroid of that triangle.
Of that triangle, yeah.
Okay.
Right. So both of these, the shape I'm talking about is the shape of the distributed load. Okay, so notice the distributed loads we're going to be dealing with are vertical. And so because you can move forces along their line of action, we're only going to need to know the horizontal centroid location. Okay, so let's do the example that I gave when I introduced distributed loads. So let's say we have a beam and a distributed load that's a triangular shape. Right at the top, it has a distributed load of 10,000 newtons per meter. And the length is 2 meters. And we want to know what are the reactions at the wall. Yeah.
What is the distributed load? Like, what is it in the middle?
What would make that?
Yeah.
The easiest way to picture it is imagine like a stack of sand sitting on it that's in that shape. That would do it. So it could be the weight of an object sitting on top of it. But it also could be, it's a little hard to picture it, this being an example of what I'm about to say, but it could be like the way, the pattern of forces that like a motor is applying to an object, you know.
Like when you have pistons and they go in different directions, it creates a
Right.
force or whatever.
Yeah, right. Like inside, for example, if you have the shaft coming out of a motor is connected to some kind of bearing system, and the loads that it applies wouldn't be acting just at a single point. It would be spread out over the, and if you did some experiments, you could figure out roughly what the pattern of that distributed load looks like, and then you'd model it mathematically with some pattern that more or less fits, similar. I mean, it's probably worth pointing out that really distributed loads are the real things, and point forces are the mathematical simplification. When like if we're trying to figure out what the forces are at this joint here, when I lean down on this, your first calculation would definitely be saying that I'm applying a point force here, but of course some area of my hand is touching the table, and it really is spread out over some pattern. And if you wanted more accurate results, you'd have to know more about the pattern that, how those forces are distributed across that. It's probably a little more right under whatever this part's called, and a little less here. You know what I mean? But the easiest way to think of it for sure is just imagine sand stacked up in that shape, and it's its weight. Okay, so first let's figure out the location where we're going to apply this point force and what that point force is. So I'll put my coordinate system here, since that's where we're going to put the origin. And now think about this shape. That's the distributed load. The height is 10,000. The width is 2. It's not drawn to scale. But that's a right triangle. And so the area is 10,000 times 2 over 2, so 10,000. And notice that the units work out because we have units of newtons per meter for the distributed load, meters for the length. So the total force is 10,000 newtons. And then for the centroid, well, what's the centroid of this shape? We only need the horizontal one. So for a triangle, the centroid's there. Where this distance is 1/3 of the way from the long edge to the point. So 1/3 of 2 is 2/3. And so the coordinates, or the x-coordinate of that centroid where that force is going to be applied, if it's 2/3 of the way in the negative direction from the y-axis, that's negative 2/3, or negative 0.667. Any questions yet? Okay, so now let's set up the table. So rho, force, moment. And our about point is where we put the origin. Oh, I skipped one thing. We need a free body diagram. Okay, so the body that we're isolating is the beam. What are the loads acting at the wall? That's right. It's a fixed joint, so we have the full force vector, call that R, and we have the couple, call that MR. And now we know that the weight force, or not the weight force, the distributed load, is going to act 1/3 of the way along the length, and it's going to have a magnitude of 10,000 newtons. That 10,000 newtons doesn't come from the 10,000 here. It comes from our calculation of the area. Okay, so for the distributed load, the row vector is negative. Yeah. So the row vector is negative 0.667. But if it wasn't, you just add the weight in addition to this stuff. And then the y position, where that force acts, doesn't matter. I'll just use 0. And the force vector is 0, negative 10,000. Take that cross product, and you get 6666.7. I don't know. Those sixes keep going. And now the force, I'll do the force R next. So this one's the distributed load. I didn't write it. It's implied in my head. I'll pull it out later. And then R, what are the coordinates where R is applied? Or what's the row vector? That's 0, yep. And the force is Rx, Ry. So there's no moment. And then the last thing we need is the couple applied at that joint. We don't care about this stuff with couples, so I'll just enter that as MR. And now Newton's second law says 0, negative 10,000, plus Rx, Ry is equal to zeros. We can solve this one right now, and it says that that R vector is 0 for x, positive 10,000 for y. And then the moment equation says 6667 plus MR is equal to 0. So that tells us that MR is equal to negative 6667 Newton meters. So we have an upward force applied at the wall and a clockwise couple. So let's think about if that makes sense. This upward force here has to counteract the force produced by this distributed load. That's going to be downwards. So it makes sense that this would have to be upwards, right? And then the couple at the wall has to counteract any rotation that distributed load is going to apply. That distributed load is trying to make this beam rotate counterclockwise. And so the wall has to be applying a torque like this to keep it from rotating counterclockwise. And so that makes sense.
It's just the opposite of the direction of the
Yep, that's right.
distributed load is moving forward.
Yep. Yes?
Beam
We are in this case, yeah. So what we're really doing is we're saying that the weight of the beam is negligible compared to this big distributed load, so we're just leaving it out. If you were given it, then you would put it in just the way you do in other problems. Just apply this free body diagram would just have the weight as a third force, and you'd still put that in, but now you'd put the weight in too. Yeah, it would have its own row in the table, yep. Okay, let's do another one. Yes?
What would happen if the triangle split, where the larger amount of force was on the end? Like in the real world, I'm thinking that's how you would break it off the wall, right? But
Yeah.
what does it look like does it change the moment then? The moment would change.
Yeah, the moment would change, and the effect would be the centroid of that triangle would be in a different place.
Oh, right. It would be over on the
So you'd go through these same steps, calculate where the centroid is, but now you'd just be applying those forces at a different spot. Yeah. Yeah. Okay, so let's say we have another beam. And there's a roller at the midpoint. And a triangular distributed load on the right half. At its highest point, the distributed load is 2,000 newtons per meter. And each of these is half a meter long. So the whole thing is 1 meter long. And let's say the mass of the beam is equal to 100 kilograms. What are the reactions? $2,000. Okay, so let's figure out what we know about that distributed load. It has a length of 0.5 and a height of 2,000. So the total force is the area. That's 0.5 times 2,000 divided by 2, so 500. And then the centroid location, I guess let's choose origin. The easiest place to choose the origin and the about point is on the left end where the pin joint is. So that's the coordinate system. So what's the x location of the centroid? Well, it's a third of the way from the long edge to the point. So 1/3 of 0.5 is 1/6. So This distance is 1/6. So let me draw that. So 1/6 is 0.167. And now in this coordinate system, if the centroid is 0.167 to the right of here, right, it's like here, what's the x coordinate of that point in this coordinate system?
0.6666.
Yep, that's right. 0.66646 with, plus or minus 0.002. Just kidding, that's an engineering joke. It's all sixes.
Question. So
Yep.
0.167 when we calculated, and why we put this, like the center at 0 point on the x-axis, and then we put 0 point, is it the whole thing, the 0.66, like the 1 meter?
This?
Yeah.
So we figured out that the centroid was 0.167 away from this end of the triangle.
Oh.
But then that end of the triangle is 0.5 from our origin. So it's 0.5 plus this gives you that.
Okay,
Yep.
that makes sense.
Okay, so now let's draw the free body diagram. This is a pin joint. So that's going to apply a force vector. I'll call that RA over here. Then there'll be the weight applied at the center. I'll put that up here just because it'll clean up the picture. That's 981. Then there's the force applied by the roller. That's going to be an upward force, also at the middle. I'll call that RB. And then last, there's going to be a force of 500 newtons here. Any questions about the free body diagram? All right, well, if the about point is here, what's the row vector for RA? 0. Forces are RAX, RAY. The moment is 0. What's the row vector for the weight? Yeah, positive 0.5, 0. And the force is 0, negative 981. So the moment is negative 490.5. What's the row vector for RB? RB is still the roller. Yep, that's 0.5 again. 0 RB, and the cross product is 0.5 RB. And then the last one is that 500 newtons. That's at the location 0.6670. You know, the y position doesn't matter. The force is 0, negative 500. And so the moment is 333.33 negative. So Newton's second law says RAX, RAY plus 0, negative 981 plus 0 RB plus 0, negative 500 is equal to zeros. And the moment equation says negative 490.5 plus 0.5 RB minus 333.33 is equal to 0. So we know RAX is 0. RB, can someone tell me what that is? What? 1648 positive. And then what do you get for RBY, or RAY, sorry? 167. Okay. So RB is 1648. RA is 0 horizontal, negative 167 vertical. Is there anything we can sanity check about those answers? Yeah, there's one of these forces that has to be positive. We know that normal force, if that value came up negative, that would say that that roller was pulling down on this body, and that can't happen. So that has to be positive, and we did get that positive, so that's one thing that gives us a little extra confidence. Yep?
Is there any particular reason why the x components of the pin joints is turning out to be 0 a lot of the time?
Yeah, because these two examples haven't had any horizontal external forces. If I had just put a force on here like this,
Okay.
We would have gotten something for that.
It just feels like it's always the x component you can solve for instantly.
Yeah,
And I don't
I should.
know why.
It's because of that.
Okay.
It's just because of the external forces. If I put external forces, x external forces on, then those values would be non-zero.
Okay.
Any other questions? How much time do we have? So let me give you one that you can work on. So let's say we have a beam with a pin joint in the middle. And a rectangular distributed load from the pin to the center of the right half. So let's say this distance is 0.5 meters. This is 0.5 meters. And this is 1 meter. And let's say that at this end there's a roller acting down. And let's put a horizontal force on this one. Okay, I'll make this distributed load 1,000 newtons per meter. What are the reactions? We'll neglect the weight. Okay, see if you can work through that one. Talk to each other. Ask me questions if you get stuck. I'm not sure. We might. I might have to wait to go through the solution until next Tuesday, but we'll see how far you get. Okay, that should be done soon. I'll go through this problem while it's doing my resume. So let's do the coordinate system here. So that's going to be our about point. The rectangle has a height of 1,000 and a width of 0.5. So the area is 500 newtons. And the centroid, the x-centroid, is at the midpoint, 0.25 meters from either end. And since our origin is at the left end, this is just going to be 0.25 meters. And now free body diagram. At the pin, there's a full force vector. Call that R. At the roller, there's a downward force. I'll call that N. Then the distributed load applies a 500 Newton force down. And then the last thing is a 5,000 Newton horizontal force there. And that's the about point. So rho, F, M, for the normal force, for that roller force, the rho vector is -1, 0. The force vector is 0, -n. And so the moment is positive n. At the pin joint, that force R is at the about point, so rho is 0. The force vector is Rx, Ry, so there's no moment. then the 500 Newton force, that's the distributed load. The row vector is 0.250. The force is 0, negative 500. And the cross product is negative 125. And then the last one is that 5,000 Newton force. Its line of action goes right through the about point, so we know it's not going to produce a moment, but it's at the point, like the row vector is 1, 0. The force is 5,000, 0, and so the cross product is 0. And then Newton's second law says 0, negative n, plus Rx, Ry, plus 0, negative 500, plus 5,000, 0, is equal to zeros. The moment equation says n minus 125 is equal to 0. So n is equal to 125. And r is equal to negative 5,000 for x and 625 y newtons. Any questions about that? Okay, well, yes. Yeah, well, n is just a value, but you're right that if you then put it into its force vector, you'd plug it back into this vector, and it would be a vector 0, negative 125. But the value is positive 125. Okay, so I'll get the assignment up soon, and it'll be some big chunk of those centroids problems. All right. Have a good long weekend.
Thursday, all the college.
Yeah, the school's closed Thursday and Friday. Yeah, on Wednesday.